All right. Good morning, everyone. How are we doing? Tired out? Got that November vibe about you. Well, welcome to EX 151, lecture 20. We're going to start talking about arithmetic today. But first, let's recall what we were talking about last time. So please go ahead and read this problem and try it on your own. Now, I will go ahead and activate the poll so you can submit your answer.
Well, I mean, that was right, man. Actually, number first.
All right, I see a few responses coming in. Let's take one more minute to think about this one and then go ahead and vote.
I guess we know that. Perceive that. Yeah, I agree. Because I think that's kind of going to be slower and yeah, that's a good. Maybe you're slower and then have guessing about that. I didn't say it's point. I think that's really great.
All right. Let me turn the mic back on there. So I'm not seeing a ton of responses so far. For those of you that have figured it out, and even if you haven't, please go ahead and turn to your neighbor and try to convince them that you have the right answer, A, B, or C. Okay, I'm gonna pause the poll. Go ahead and talk to your neighbor.
Maybe the next candidate. Yesterday we talked about how you might hear example. Good job. Wait, what's the guy? Oh, shit. I knew you were talking about that.
All right, let's come back together on this one. Raise your hand if you feel like you and your partner got to an answer that you feel confident about. Okay, not that many. So let's talk about this together. And I'll go to a blank slide so we can draw if we need to. So what answer did you arrive at?
So, I mean, we were first kind of contemplating with the question we're even asking, like, if you reduce frequency, the life will be longer, but you'll still get the same like output out of it.
Okay.
So that's what we were like.
Yeah, so we're doing the same amount of work regardless of the frequency, right? Because we always need to do this 1,000 cycles. Okay, so that's so far so good. If we're trying to extend battery life, if that's our primary concern, does that mean we're trying to optimize power or energy here? Yeah, this is tricky, but it's kind of key to understanding the whole thing, right? So a battery stores a fixed amount of energy, right? So if we're trying to optimize battery life, we need to somehow improve the energy that it takes to do this amount of work, right? The amount of work we need to do for the image processing is known, it's fixed. So that's kind of a known quantity. And the power doesn't matter as much. What matters is the total energy, right? Which you, again, from last time, you can think of as the area under the curve. So if I think about, I like to reason about these thinking about power over time, right? So if we think about our 1,000 cycles, and remember, there's two different components of power, right? There's dynamic power that is spent only when you're doing the work, but then there's leakage power that's just kind of always getting sucked up in the background. So let's say 1,000 cycles, it takes this long to do the work. And you have your leakage component. And then you have your dynamic component. Dynamic power is typically bigger than leakage power when the chip is on, right? When it's actually doing this image processing. And so then the energy would be the area under this curve. Just conceptually, we haven't put any numbers to this, and we don't actually need to answer the problem. So can someone remind me what the dynamic energy equation that we gave last time was? Yeah, there was an alpha in there. What else? C BDD squared. There's no frequency component to energy, right? Energy is independent of frequency because it just has to do with how many times you toggle the transistors, right? If it's 1,000 cycles, it doesn't matter if you're toggling once per second or once per millisecond or once per nanosecond. It's still 1,000 toggles. It's still 1,000 discharges of those capacitors, right? So if you think about what this means in terms of the problem statement, this is your colleague's proposal. Let's run at half the frequency, so the workload takes twice as long to finish. The dynamic energy is going to be the same, right? The area of this box is going to be the same as the area of this box. The two stars, which I'll mark to be clear what I'm talking about. It takes twice as much time. It's consuming half as much dynamic power over that time, but if you integrate it, the energy is the same. But now what's happened to our leakage power, our leakage energy, rather? It's doubled, right? Because our time has doubled. So if you decrease the frequency by half, this is actually worse for battery life, right? Because it's taking you longer to do the same amount of work in the same dynamic energy footprint, but you're just integrating more and more leakage over time. So this is, remember what I said on Tuesday that, it's the difference between energy and power sounds very simple or trivial, but it's actually a really important concept for digital designers. And this is a kind of a classic mistake. It's like, oh, I want to make my battery go longer, I'll just slow it down. But unless you also decrease voltage, slowing down doesn't help your battery life. And in this case, we were told that we can't decrease voltage because we're already at the minimum voltage. Yes. Yeah, so we gave a formula for leakage current last time. The details of the formula are not actually important for this problem. It is highly dependent on threshold voltage and on temperature, so it's exponential with those terms. But in general, as an approximation, you can assume that once you've taped out a chip, it's basically going to have a fixed amount of leakage. Whenever you turn it on, it's going to be leaking that amount. Yeah. There's some subtlety there, but you can think of it as just being an intrinsic property of the chip and the transistors that you decided to use. Yeah. Exactly. Yeah. Yeah. Correct. Yeah. Yeah. When we talk about battery life or battery capacity, it's always measured in units of energy, which again, confusingly are often this very weird unit called kilowatt hours, which is it's a power times a time. So it is a unit of energy, but it looks like power if you first glance at it. But yeah, if you are thinking about preserving battery life, then you should always be thinking about energy. Now, if we were asking which of these designs has lower peak power, obviously the second one would be better. But for smart glasses, you probably don't care that much about your peak power because it's only going to be in the milliwatt range. You're not generating a lot of heat. So you mainly care about getting the energy per operation down. Okay, any other questions about this? The gears are turning. Can folks give me a fist of 5? How are folks feeling about the power and energy content that we talked about last time? 5 is all makes total sense. 0 is I skipped that lecture. I don't know what you're talking about. Okay. So people are feeling pretty confident overall. You'll get some more practice on your homework and in the discussion sections this week. Okay, so now we're moving on to a new topic, which is arithmetic and specifically addition. That's what we're going to be talking about for the rest of today's lecture. Now, some of you may be saying, well, I already know how to add two numbers in a digital circuit. Here's the Verilog. Assign sum equals I0 plus I1, where these are 32-bit numbers. And congratulations. Your synthesis tools or FPGA tools will instantiate an adder for you. So you're absolutely right. Good point. That concludes today's lecture. Thank you all for coming. No, today we're actually going to talk about how you actually build this thing, which I think so far has been a little bit of a black box, right? We've had these adders sitting in for example, our processor microarchitecture diagram. We described them at the register transfer level, the higher level of abstraction. But today we're going to go in and see, well, how do you actually build this out of gates, out of transistors, which we haven't talked about yet. And it turns out that the answer, like so many things in digital design, is all about trade-offs. So first of all, it depends how many bits you're trying to add together. And then it also depends on what you're trying to optimize for. There are different answers to this question, best answers, depending on whether you're trying to optimize for the triangle, the holy triangle, right? What is it in digital design? What are the three? Performance, power, area, right? So today we're nudging down the level of abstraction a little bit. We're peeling back the curtain, and we're going to learn what actually goes on inside an adder and how to design a good one. Yeah, adders are probably the topic in this course with the most history out of everything we're going to be talking about. You know, a lot of digital design, it's not radically new, but most of it was invented within the last 50 years or so. But the automated arithmetic and the ideas behind it go back way longer. So if any of you have heard of Charles Babbage or Ada Lovelace, who was the first programmer of this machine, this thing is called the difference engine. This is actually difference engine number 2, which Babbage never finished building in his lifetime. He tried to build it, but ran out of time and money. But after he died, people went back and looked at his notes and built the thing and proved that his design was sound, that it actually worked. And so you can, if you want to really nerd out about this, you can go to the Computer History Museum in Mountain View and see one of the working models of difference engine number 2. So these concepts that we're going to be talking about today, some of them go back centuries, where people have been thinking about how to add numbers automatically, even before there were any digital circuits or electrical concepts in which to do it. This design is entirely mechanical, right? But the core concepts are there. We're going to talk about some of them today. So let's start with one building block that you have seen before in previous parts of the lecture. This is a full adder cell, a single bit full adder. And so basically it has 3 inputs, right? A carry in bit, CI, and then the A and B, the 2 bits that you're trying to add. And then out of that, you get an S, which is sum, and CO, which is carry out. And the truth table is shown here. There should be nothing shocking here, basically, right? If you have a single 1 in any of your 3 inputs, which are all treated symmetrically, they're treated the same, then your sum is 1, but your carry out is 0. If you have 2 1s, then your carry out is 1, and your sum is 0. And if you have 3 1s, then your carry out is 1, and your sum is 1. And so we can write the Boolean logic functions for sum and carry out. Sum is just the XOR of the 3 inputs, which is also called a parity checker, right? Because it's true. I guess it's actually an inverse parity checker. It's true if the number of 1s is odd, and false if the number of 1s is even. And carry out, you can think of is also called a majority gate, because it's true if majority of the inputs are true. So this cell is going to be our building block of what comes after. But from a single bit perspective, it's pretty digestible. It's pretty understandable. Here it is as a single giant logic gate. So this is probably more complicated than any logic gate you've looked at before and might seem a little intimidating. But this is a real design. These full adder cells are so important that they will go ahead and build a big logic gate out of 28 transistors just to do this functionality. I'm not going to step through all the details of exactly what this is doing, but you can see that on the left, the logic functions have been kind of decomposed or written in a more convenient form that renders them amenable to being realized as gates. And in particular, you see that this is an equation for Cout bar. And I'm going to highlight that this logic gate is actually made out of 4 different ones. So it's not a single stage, right? So this first one that I've highlighted is calculating Cout bar, which is labeled as X here. And then it goes just through this little inverter to get Cout, right? So that's 2. And then we use that carry out bar, carry out negated in this big old thing over here, which calculates S bar. And then that is inverted to get S. Okay. So typically this will be assembled in a standard cell library as a single big standard cell, but it actually has 4 different stages inside of it that are cascaded in this way. So this is our full adder cell. So far, so good. Let's talk briefly about administrivia, and then we'll talk about how we use it. Okay, because I ran out of time for this last time, and I don't want to miss it. Time to be working on those projects, as you know. FPGA and ASIC checkpoint 2 are due tomorrow. Hopefully everyone has started. Yes. Okay, good. Good. That's if you haven't started, please do. If you have started, please keep working on it. I want to make another appeal to not just tomorrow when I'm sure the lab sections are going to be totally slammed with people trying to get checked off, but please continue to attend your regular lab sections. Not just like right before the deadline or when you're trying to get checked off. It's really useful to have a space where it's easy to get help and talk to your peers, and just to have some dedicated time for you and your partner to sit down and work on the projects that's like carved out of the rest of your busy schedule. So please do go to lab section unless you have some extenuating circumstance. And then lastly, just a reminder that next Tuesday is Veterans Day holiday. It's a Berkeley holiday, so no lecture and also no office hours, no lab sections. Everything is canceled on Tuesday, but the rest of the week is as normal. Okay, any administrative questions? All right. So then let's talk about how to use this full adder cell to build a multi-bit adder. The simplest way to do this is just to chain them together. So this is about as straightforward as you might imagine. Remember that we have each of these full adder cells has a carry input from the previous bit. And so we can just attach the carry output of bit 0 to the carry input of bit 1, and so on, all through the chain. So this diagram shows a 4-bit adder. This design is called a ripple carry adder. The naming is pretty straightforward. It's because the carry signal has to ripple from the first cell all the way through to the last one. And if we think about the worst case delay of this design, it's not great, right? Because for every bit, we're adding another stage that the logic has to propagate through. In particular, the carry has to propagate through. So if you think about the critical path, right? Well, this carry in is going to be always set to 0, right? At least typically the input bit is set to 0, right? And so if you think about the critical path, you're going to have A and B coming at the input. You need to calculate the first carry out, and then the second carry out, and then the third carry out, and then the sum. Whether you need the fourth carry out or not depends on whether you're looking for a 5-bit output or a 4-bit output, right? Because when you add 2 4-bit numbers together, you can potentially get a 5-bit result. Your logic may care about that, or your logic may just discard the 5th bit. But nonetheless, as we saw in the design of the full adder cell, it takes longer to calculate the sum than it does to calculate the carry. So this is going to be our critical path. And in general, for any n-bit full adder, the critical path is right n-1, which is here, n-1, the time needed to calculate the carry, plus the time to calculate the sum at the last stage. So this is the simplest possible adder you can build. It works. It's very functional. It's very slow, especially for wide widths, because every time you want to add a new bit, you add a new stage of delay through that carry path. So the rest of the lecture is going to be how can we make something faster than this? We can make some at least minor improvements to the ripple carry design. One nice property of the full adder cell is that it's symmetric on its inputs. And so that means it has this inversion property that the sum of the inverse of the inputs is equal to the inverse of the sum. And so we can make a sort of inverting version of that full adder cell where we recall we had those little inverters sitting on the end of the carryout. We calculate carryout bar, and then we invert it to get carryout. Well, if we want to be a little clever, we can just use carryout bar directly in the next stage and skip that inverter, right? So this is our in sort of inverting carry full adder design, if you like, where we really calculate C out bar 0 and pass it to the next stage, and then calculate the inverse of the inverse, which is just C out 1 and then C out bar 2 and C out 3. So that saved us a little bit. We saved an inverter delay on that critical path. But if you think about from a computer science perspective, from a big O notation perspective, it's still big O of n, right? It's still delay is proportional to the number of stages. Okay, sorry, let me pause for questions here about the full adder cell or the ripple carry adder before we go to a quick exercise. Any questions? Yeah.
We have to add a bunch of inverters for the odd cell input sequence.
Correct. Yeah, we do, but which costs a little bit of area perhaps. But do you see why it doesn't cost us any delay? Right? Because we assume that all the A0, B0 through A3 all arrive at the same time. So that means you can calculate all those inversions in parallel while you're waiting for the carry to propagate. Yeah, so one trick in general with analyzing these types of adder designs is there's often a lot going on in parallel, but from a purpose of delay, we only care about optimizing the critical path. And so we often try to offload computation off of the critical path in order to shorten the critical path. And that's basically the trick that we're playing here. Okay, good question. Any others? Okay, please go ahead and try this problem on your own. It looks like the poll is not fully displaying, but hopefully when you scan the QR code, you should be able to see all the options. All right, so I have opened up the poll. So if you've figured out the answer, at least to the first question, please go ahead and vote. We'll take a couple more minutes here.
I think they. No, I was just serious. I don't think you. I know, I'm sure there is a way to do that. I don't know, ultimately, like, gives us more or worse. Wait. Because I thought maybe there was a way to use it to, I thought it was. Yeah, that's good. Like maybe calculation. Person. I know it's from TLT. I'm very calculation.
Okay, give me a thumbs up if you voted. Okay, what about everyone else? Go ahead and scan the QR code if you haven't. Take 30 more seconds and select the right answer, and then we'll discuss.
Yeah. Yeah, I don't think.
Oh, it's gone. Let's try this. Yeah. All right, well, poll everywhere is getting a little confused about itself, but hopefully folks can see that most people selected B, which is 1 half adder, 3 full adders. So people correctly noted that that first cell, the carry in, is not used. And so you can replace that first cell in the chain. Here, we'll try it out here. All right, you can replace that first cell in the chain, the half adder. And then the other 3 still have to be full adders to handle the carry. Regarding the bonus question, I was able to come up with a 16 transistor half adder cell. So there's an easy way to build it in 18 transistors, and then there's a slightly more clever way to build it in 16 transistors. I believe that's the best you can do. So that compares to the 28 transistors for the full adder. So it's a pretty big savings just from not having that carry in. But it's not quite 2x, which means that it's generally not going to be worth trying to replace a full adder with 2 half adders or anything like that. Cool. Any questions about this one? Yes. Oh, I won't show a transistor diagram, but let me briefly write the Boolean equations, which hopefully folks can read off of the diagram pretty easily, right? S is just A XOR B. And carry out is just A and B. Yeah, that shouldn't be a shock. So We haven't talked about how to build XOR out of transistors, but a typical implementation is a 12 transistor implementation. There's a few different ways to do it, actually. There's not a single best way to build an XOR gate. And then an AND, how many transistors is an AND gate? 4 for NAND, right? Yeah, because CMOS is always inverting. So this is 4 plus 2, this is 6T. So this is what I was saying. The easiest way to do it is just to build 2 separate gates, and then you can get 18 transistors total. I found a way to combine some of the parts of them in order to get 16 instead of 18, but I will leave that as an exercise to the interested person, because we need to move on and talk about more types of adders, unless there are more questions on this. Yes. Yeah, so let's go back to PowerPoint is getting a little grumpy. All right, let me go out and back in real quick so I can select the right slide. Yeah, let's go back to this diagram. So recall that we have the carry out is calculated in this first gate, but it's really carry out bar, right? The inverse carry out, and then we pass it through an inverter to get carry out. And so the optimization is just saying, get rid of this inverter. Just pass carry out inverse directly into the next stage, and then invert all of the other inputs of the next stage as well, and calculate the sum and carry out based on that, right? So it's alternating inverted, non-inverted, inverted, non-inverted. And it saves, it's not a big savings, but it saves the inverter gate delay. Okay. Okay. We're going to take a little 20-second break because PowerPoint is having its daily meltdown. This break has been sponsored by the Microsoft Corporation. All right. Okay. So we're moving on from ripple carry adders, which are the simple, easy, slow, right? We're going to start talking about how we build the real adders that get used in actual practice. For example, in the CPU designs, when you write down A plus B, it's definitely not going to build you a ripple carry adder for your 32-bit adds in your ALU. It's going to build one of these other kind of adders that we're going to talk about. So all of the adders that are more advanced than a ripple carry adder use these special intermediate signals that we're going to go into detail on this slide, called generate, propagate, and kill. They have kind of, it's kind of funny names, but hopefully after we explain them, it'll make a little sense why we call them these things. And so let's go ahead and write down first the logic functions for generate, propagate, and kill based on this truth table. So generate is true only if A and B are true, right? So generate G equals A, B. Propagate is true if A or B, but not both, are true, which is XOR A, XOR B. And then kill is only true if A is not true and B is not true, right? So why do we give them these funny names? Well, think about what this means in terms of the carry signals, right? So generate is saying if the inputs are both true, then that bit is always going to generate a carry signal. The carry out is always going to be 1, regardless of what the carry in is, right? So it's generating a new carry in that bit position. Propagate is saying if exactly one of A or B are true, then it's going to propagate a carry signal from the carry in to the carry out, right? It's going to pass it through. And kill is saying if A and B are both 0, then no matter what the carry coming in is, the carry out is always going to be 0. So it kills the carry propagating along the chain, right? Now, we can write the carry out in some equations in terms of generate and propagate, again, based on this same truth table, which I'll do now. So carry out, to put the words I just said into logic equations, is either true if generate is true, or if propagate is true and carry in is true, right? We either generate a carry or we propagate the one that comes in. And then sum is less important because it's not on the critical path for the most part, but we can write down the equation. Sum is propagate XOR carry in based on the logic table. The critical thing here is that these generate, propagate, kill signals, if you scrutinize the logic functions, they don't depend on the carry input bit, right? They only depend on A and B. So that means as soon as all of the A and B arrive in parallel, all 8 bits or 32 bits, however wide your adder is, all of those A and B arrive, we can immediately calculate, generate, and propagate and kill for all of the parallel structures in the adder. And that's going to save us a great deal of time compared to the ripple carry. And that's the key idea that's going to be exploited in all of the fast adders we're going to talk about today. So, right, we notice a couple of things. As I said, generate and propagate only depend on A and B. So we calculate them in parallel. And then we also notice that once we have generate and propagate, carry out is very simple to calculate. Right? In fact, it's this exact AOI gate, 6 transistor AOI gate that we looked at a couple lectures ago for a different example. So let's look at an example of how we can use generate and propagate and kill in order to speed up our adder. Now, this design is called a carry bypass adder, also sometimes called a carry skip in textbooks or in the literature. Notably, this is the design that Charles Babbage came up with for his difference engine. So you're learning something here that was first figured out even before transistors or really electrical circuits were invented, right? But the concept is still sound. Okay? The idea is that we're going to group the full adders into groups of 4, right? So we have these chains of 4 full adders. And then at the end of each chain, we're going to have a multiplexer, a select between 2 options. And we notice that, the propagate signal kind of, you can think of it as propagating all the way along the chain, right? So if the carry in comes at the start of this chain, it's only going to affect the output if all 4 of those propagate signals are true, right? It's only going to affect the input if all 4 of those full adders are saying, yeah, propagate the carry that came in to the next stage, propagate the carry 4 times. And so we'll add a select signal on the mux that says, if those 4 propagate adders or those 4 propagate signals are true, then we don't actually need to go through the full adders at all. We can bypass them and just go straight through the multiplexer, through the short path of the multiplexer. Right? Because this is we know that based on those 4 propagate signals, carry out is going to be equal to carry in if they're all true. If they're not all true, then we need to look inside the full adder cells and figure out, okay, is this a generate situation or is this a kill situation? But again, we can do that off the critical path. And so that's not as big of an impact on delay. Okay, let me try to illustrate what I mean by calculating the critical path for the carry bypass adder, which is going to be considerably more complicated than the ripple adder, but you're going to see how it saves us time. Okay, so keep in mind in these setup blocks, this is where we're doing the propagate generate calculation for each bit, right? And all of that is happening in parallel. So the bits arrive, we calculate P and G and K. The critical path is going to be doing the calculation for the first set of bits, 0 to 3. So our critical path has T setup. Then we do need to actually do, in the worst case, the carry propagation for those first 4 bits, right? Right, so we go through this first block like normal. So we have M bits in each group. In the example I just showed, it was 4. Okay, now here's where the magic happens, is in parallel, we've already calculated the generate and kill signals for all of the downstream blocks, right? So that means that in the best case, we're choosing the top select of the mux. In the worst case, we're choosing the bottom select. But even in that worst case, we're not going through any logic. We're just going through a mux in each stage, right? So if you look at how many bits, how many stages there are compared to N and M, well, there's going to be N over M stages. And then we skip the first and the last. So it's -2. T bypass is just the time through the mux. We're not doing any other logic there. And then finally, we need to go through this last carry propagation block to get the bits needed to calculate the final sum. And so we have another M T carry, and then T sum at the end. So this is the critical path. This is the worst case. This worst case won't always happen depending on our inputs. But as you know, we always need to determine our timing in our digital circuits for the worst case, right? So this is what you would declare as the delay, the worst case delay of this circuit. And we notice that that delay is no longer proportional to N. It's not N stages. It's now N over M, right? So because we're calculating these groups of M bits, we're calculating the propagate, generate, kill signals in parallel. We're dividing the propagation time by M, which is a big savings over the ripple carry, as long as you don't worry about all these constants. Okay, questions? Yeah, so this is N over M. Let's just do concretely for this example, right? So in this example, N is 16, which is the total number of bits. M is 4, which is the number of bits in each stage. So the number of stages is equal to N over M, which is also 4 in this example. So this N over M term is just the number of stages in the carry bypass header. Yes. Why is it -2? Yeah, because the number of times that we go through this bypass critical path through the muxes. Well, I guess yeah, I guess it's assuming that this mux is counted as this first mux is counted as part of the carry propagation delay of the first stage. And so it's basically just counting from here to here. So it's T bypass times 2 in this example. If you want, you could do bookkeeping of counting that first mux in there as well, and then it would be n over m minus 1. Other questions? Yeah, this one takes a little while to wrap your head around. So don't feel too flummoxed if you're not seeing it right away. The key concept is that we can calculate all of those GPK in parallel from the start, and then each stage has them ready to go as soon as the carry gets there. And it can either immediately just send generate or kill into the mux and selects that, or it can propagate the carry in, bypassing all of the work that was already done for that stage. So the question of when this is better depends a lot on, when that n over m term comes to dominate, right? Which is basically the shallower slope of the bypass adder versus the ripple adder, right? You can think of this is the slope n, and this is the slope n over m. But all of those constants add up, right? So for very small bit widths, the ripple carry actually is faster because you don't have to do all this extra work of calculating the propagate generate signals at the start, right? That fixed overhead that applies. And so as suggested in this plot, the typical trade-off point where a bypass adder becomes faster than ripple adder is somewhere around 4 or 8 bits. Depends a lot on the process technology, on your design constraints, on the details of your implementation. But certainly for very wide adders, the bypass is going to win every time because of that shallower slope. Okay, any other questions about carry bypass? All right, time for break. Oh, it's not unanimous, interestingly.
How is it not adding to them?
Yeah, I guess it doesn't quite display properly at the bottom there. Okay, I thought this would be the one question that everyone gets it right, but oh, we've shamed people into changing their answers. Okay. Okay, we're so close. Oh, oh yeah, we did it. Nice job. Okay, I'm gonna turn it off before someone messes it up. Yeah, I mean, I see no issues. Okay. For the remainder of the lecture, we're going to talk about the coolest kind of adders, which are these carry look-ahead adders, also called parallel prefix adders. So I want to talk at a high level about the structure of these parallel prefix adders first, just so you have some sort of conceptual framework when we start getting into the nitty-gritty details in a moment. So parallel prefix adders always look like this, some flavor of this, right? So step one is calculate those bitwise, or for every bit, propagate and generate signals in parallel. Okay, and this is, I'll just make a note. This step is easy or trivial, so we don't really talk about it further. You can see it's pretty much the same for every bit. It's these very simple gates to calculate P and G based on the very simple logic functions that we gave a few slides ago. Step 3 is also easy, so we'll do that next. Step 3 is calculate the sum bits. And you can see again that structure it's just an XOR. It's a very regular structure, again based on the equations that we gave previously. So we have this kind of missing step 2, which is the complicated part, which is where we're going to spend the rest of the time talking about. So what we need to do in step 2 is calculate what are called group generate signals. And this is the tricky bit. And this is the part where there's lots of room for optimization and different optimal design points, multiple different solutions based on whether you're trying to optimize for power, performance, area. Because there are many different ways to calculate these group generate signals in order to get the relevant collateral for the sums. Okay, so let's get into the core concept of these look-ahead adders, right? So we said previously that we can calculate the generate and propagate signals, which we do in that first stage. We can also calculate kill. Most designs don't actually use kill, so we'll just focus on PG for the remainder of the lecture. And then we know that based on each stage is carry in, you can use propagate and generate to calculate the carry out, right? So carry out, carry in 0 comes in. We can use propagate and generate to calculate carry in 1, carry in 2, carry in 3, carry in 4. So far, so good, but we haven't actually helped ourselves really, because you can still see that we have this rippling property in this sort of basic design that we've shown here. This is effectively just another ripple carry adder, just refactored in terms of PG, right? Where that carry is still rippling through every stage. You need to get carry in to find carry out for each bit. So no help so far. Let's try to do something a little more clever, right? So we can think about how to express what I just said in terms of equations. Right, so we know in general that the carry out bit is equal to the generate plus propagate times carry in. And we can rewrite that with the carry in expanded as the carry out of the previous stage. So that's generate of stage 1 plus P1 generate of stage 0 plus right, and we can go ahead and expand this out if we want. So I'm just writing in equations what I said in words on the previous slide, right? We have this sort of hierarchical progression where we calculate the first term based on carry in bit 0, and then use that to calculate the second term based on carry in bit 1, and so forth. And so in general, for the kth bit, if we generalize this, right, it's going to look like the generate of k plus the propagate of k. It's the generate of k minus 1 plus propagate of k minus 1, the carry in of k minus 1. And we, if we want, we can keep expanding this out recursively. And we can go down to k minus 2. And so on. We can continue to expand that equation out recursively all the way down the chain. But again, just restating an equation is what I said in words on the previous slide. We haven't helped ourselves. We still have this, the recursion is the problem that we're trying to get out of, right? Recursion is saying each bit depends on the carry of the bit before it, which is what we're trying to avoid. So let's try to be a little more clever and come up with this idea of the group propagate and generate signals, right? So we already actually looked at group propagate from the carry bypass adder, right? The propagate is true for a group of bits if the group as a whole propagates the carry to C out, right? So it's just the and of all of the bitwise propagate signals. The group generate is true if that whole group generates a carry. The group generate is true either if the last bit in the chain generates, or the last bit propagates and the second to last bit generates, or the last two bits propagate and the third to last bit generates, and so on until you reach the end of the chain, right? So do you see how we can define these propagate and generate signals for groups of bits rather than just for individual bits? And then we can define where capital P and capital G are group propagate and generate signals. We can just say that the carry in for that group either depends on, or the carry out for that group depends on whether that group is a generate or that group propagates the carry input. And just like the bitwise propagate and generate, the group propagate and generate signals or levels can be determined, pre-computed ahead of time for the whole set of bits that are our inputs. Yes.
Like the group propagate and group generate signal, are they like single bit?
Yeah, right. So it's going to be a single bit for that whole group, saying whether that whole group propagates or that whole group generates. Okay, so we can calculate these group propagates and group generates. That seems like it might save us some time. And then we can apply even more cleverness and calculate them hierarchically, right? So in this example, which, by the way, I'll call this a radix 3 look ahead adder design. I'll define that more precisely in a moment. But for now, just notice that each stage has 3 bits of input, right? So for this radix 3 carry look ahead adder design, we calculate based on the first 3 bits, a group propagate and a group generate for the first 3 bits, which we call PA and GA. And then a group propagate and a group generate for the second 3 bits. Group propagate, a group generate for the third 3 bits. But then we can actually apply another level of hierarchy, right? And we can define a group propagate for those whole 9 bits, which is just the and of those ABC propagates. And we can define a group generate for those 9 bits. And you see that once we've done all this pre-computation of P and G, then we can immediately figure out, as soon as we have carry in for bit 0, we can immediately figure out what carry out for bit 9 is going to be based on all that pre-computation. So we no longer have a ripple, right? We no longer have a recursive property or a need to look bit by bit at how the carry flows through each bit of the design. Rather, we pre-compute these group signals and then use that to determine in large chunks how the carry moves through from the early bits, the LSBs, to the later bits, the MSBs. And so key to this concept is the idea that we're building this tree of gates. Remember, in step 2, I said our goal was to calculate the group generate signals, right? And that's exactly what we're doing here. So we're building this tree of gates to calculate bigger and bigger groups of P and G. And then we use those to calculate the sum at the end directly, right? We don't actually need to ripple any carries through the chain. So we call this a look-ahead adder because effectively, as we pre-compute these bits, we're looking further and further ahead in the design, or in the tree rather, to figure out what the carry is going to be as we progress further and further toward the MSB. And as we've seen, it's advantageous, rather than calculating the groups kind of recursively one after another, it's advantageous to group them into trees like this, right? Because we know that if you look at a tree structure to calculate these group propagate and generates, those trees give us this really nice property that they're now big O of log base 2 of n rather than big O of n, right? So in this example, which is radix 2, hopefully people see what I mean now by radix. Radix is the number of group propagate and generate calculations that you're kind of combining or merging in each stage of the tree. So in this radix 2 example, it has 8 inputs, but only log base 2 of 8, which is 3 stages. Okay, so we've taken the seemingly intractable problem of the carry out bit of each stage depends on the carry input of the previous stage, which is a big O of n. And we figured out, hey, we can actually pre-compute for the whole set of bits that we're interested in. Is that carry going to propagate, or are we going to generate a new one? And by doing that hierarchically in this tree structure, we reduce that pre-computation to log base 2 of n. So for very wide adders, this is obviously a big advantage over a ripple carry, or even over a carry bypass. Okay, from big O standpoint, carry bypass was still big O of n, right? It had a constant scalar, but the trend was still linear, right? Whereas this trend is no longer linear; it's sublinear, it's logarithmic. Okay. While you're digesting that, please go ahead and argue with your neighbor about this question. Go ahead and take 2 minutes. Get started now.
Yeah, exactly. You get better. Yeah.
Okay, please find someone to talk to if you haven't already. Folks in the back. Look around.
I'm thinking like how much space.
So you're saying what I would ask that.
Yeah.
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 Power performance area.
Yes. How good performance
Okay, area, so let's talk about performance.
Performance. Power. Okay, power is. I think area. Area. Yeah.
The area.
Critical area is like but then for area is longer.
I mean, power.
Number transistor.
Okay, let's come back together. Did anyone have a disagreement with your neighbor about the answer to this question? Or we got to some consensus? Okay, thoughts. I want to hear from someone in the back half of the room. True or false? Yes.
I guess probably 30, but I think it's false. Like, say like, you know, like some of the blocks are updated, some are generated, some are going to mismatch, and you just have to lot of them. Okay, but you don't have your essentially.
So it may be false because there's more logic for the prefix structures. Any other opinions? Agree, disagree? Yeah. Depends on the application. Interesting. Say more. Yeah, right. So that's the crux of it, right? So far we've talked about performance only, right? So I think from a performance standpoint, I think it would be pretty safe to argue that tree adders are always going to be better than ripple carry adders for large N. They will always be faster. You'd have to do a spectacularly bad design in order for that not to be true. What about power and area? I think ripple carry is probably cheaper for area and for power, right? It's dead simple. It's just this chain of full adder cells. Power and area often correlate, not always. In this case, I think they correlate pretty well. Right? So if you think of the number for power, if you think of how many gates are toggling, for a 32-bit adder, well, it's exactly 32 of these full adder cells. For a prefix adder, right, you're going to have this tree structure plus the step 1 and step 3 of actually doing the calculations. And so that tends to be more expensive. So I think it is false, but it depends what you mean by better. For the last 5 minutes here, we'll just do a quick tour of different kinds of tree adders. I often think of this as sort of an exercise in botany because there's just like many different species and they all have different names. We'll talk about a couple of them today. I would refer you to the Westy and Harris textbook is kind of the Bible on arithmetic circuits. So if you really want to get into it or need to do more reading to understand it, that's the place to turn. But there are many ways to construct these tree adders, carry look-ahead adders. They're often named after the people who first invented them. Or hyphens of multiple people who came up with them. Radix, we talked about previously, is the number of bits that are combined in each PG gate. So we gave we showed radix 2 and radix 3 examples. I think 2 and 4 are probably the most common in practice. Tree depth is straightforward. It's just the number of stages in the tree. And then sparseness, which we haven't talked about, but we'll, if time permitting, we'll illustrate an example. So when defining these arithmetic circuits, you'll often see these kinds of tree diagrams. These can be a little bewildering to look at, and you can't actually understand all of the details about a design just by looking at these, but they're intended to give you a flavor of the structure of the tree, right? So in these tree diagrams, how to read these, this is the number of bits. So this is bit 0 of the input. This is bit 1, bit 2, and so on. This is a 16-bit adder that we're looking at here. And then this axis is sort of conceptual delay or conceptual time. And so you can see how things are being kind of combined in this hierarchical tree. Each of these dots is one of these PG calculation blocks, right? So you can see in this design, you can read that it's a radix 2 because each dot is combining 2 inputs only. And this particular variant is called a Kogge-Stone adder. And you can see that the tree has 4 stages, and then in the diamond at the end is the calculation of the sum. Now this is what a radix 4 Kogge-Stone adder looks like. It's a denser structure. You can see that each dot is now combining 1, 2, 3, 4 propagate and generate signals from the previous stage to get a group PG for that level of the hierarchy. So the disadvantage is that each stage is more complicated, but the advantage is now we're down to only 2 stages, right? So again, you cannot read off of these diagrams which one is faster or better. This is just a way to visualize the sort of logical structure of the trees. This is what a sparse radix 2 tree looks like. So this is interesting, right? There's a lot fewer of these PG cells, but then we notice that the logic to calculate the sums at the end is going to be more complicated because each 2 sums now need to be calculated based on 1 group generate signal that's been found at the end. So is this better? Is this worse? Depends on the details. You have to go in and actually analyze it. But that's basically how we visualize some of these tree structures in different flavors. Okay, so we're out of time, but to summarize very briefly, you now, at the end of this lecture, know how to add 2 numbers together. Congratulations. Next time we will be talking about how to multiply 2 numbers together. So that's it for today. Thanks, everyone.